Hi, check out what I found deep in the bunker. This is an interesting bit of kit. Does anyone know what this is? Bueller. It might help if I take this top part here off, because this is actually not part of the original product. It's actually like a custom interface for this thing. And it's got two really dodgy binding posts here from a company called Electrodynamic Systems, made in the old Dart. Hi to all my viewers in the old Dart. They're not around anymore. They were actually bought out by Brule & Kerr. So we just have a look at the top here. Seems to have like a threaded port for like tubing or something like that. There's like two acrylic pieces like this, and inside seems to be a black disc. Get it apart, and I think I'll be able to show you exactly what this does, because at the moment it's not going to do anything. Now this is actually a bit of kit. Well, not this specific one. I used to use these all the time when I worked in the military stuff, and also the seismic underwater stuff as well. So these were bread and butter, and there's only a couple of manufacturers, probably a handful of manufacturers in the world of these sorts of things. If we take this off here, you can see that this has like a rubber membrane, and it actually was attached to this, like it was glued down and attached to this at one stage. So let me get the rest of the screws out, and then I'll show you what this does. Okay, so let's lift this off, and when you buy this thing, this is how it comes. It actually looks like this. It's got screw mounting holes in the side. These are just fillers. It's designed to actually mount into a big huge heavy block like this on like a tilt basis like this. In fact, they do actually sell the bases to go along with these things, but yeah, these are just protective caps on there. But what this is what's called an electrodynamic shaker. It's basically a permanent magnet shaker. Well, this particular one, the lower end ones like this are permanent magnet shakers. So it's basically a big grunty speaker that you attach stuff to, and you feed in your signal here, and it will have a large amount of movement here. And these are, as the name suggests, electrodynamic shaker. It's a vibration shaker motor for testing PCBs and electronics and products and things like these. And this is probably the smallest one you'll get on the market. This is the runt of the litter. I've used ones, and here's a photo. Like they're the size of a car, and they're designed to shake massive products. And this is where we would get our products tested. We would like hire the facility. There used to be a facility out at Australian Defence Industries at St Mary's that I used to go to. They actually had one of these gigantic car-sized shaker tables, and then we'd take our products in there, and we'd have to design custom mounts for them. We'd attach them on there. We'd hook up all the accelerometers, and we'd actually measure the performance over a vibration envelope to see if our product breaks, and designed to simulate transportation by road, rail and air. And there's various standards for this, that how products are supposed to survive vibration caused by transport of these different transportation systems. So what you typically get with these things is like a metal plate. It can be like a round or a square metal plate or whatever, and then you securely mount your product on top. You might have to design like little custom clamps or whatever you want to do to attach it securely to the plate so it doesn't rattle around, because that's what this is designed to do, to give you a precise rattle input, a precise vibration input, which then transfers onto your PCB, and you'll shake your PCB like this, and you'd sweep it over frequency. Usually it's from like, a couple of hertz up to 10 kilohertz, something like that. And then you'd shake it in this axis, then you mount it again, you shake it in this axis, and then you mount it again, you'd shake it in this axis, and you can figure out any vibrational modes on your PCBs. If there's any heavy components, for example, that might actually fall off when they hit a certain resonant mode. Because basically, every board, every mechanical system is ultimately going to have some vibrational mode to it. And in teardowns and stuff, you've no doubt heard me mentioning like TO220s like this that are what I call flapping around in the breeze. They're not actually mounted down. Now, like a freestanding part like this TO220 here, this will actually have a resonant mode. And if you mount on longer legs, it's going to be worse. And the more mass it has, the worse it is. So you could actually shake this thing. And if you get it at a certain frequency and a certain axis, these TO220s can actually fatigue and break off completely. And I've seen this happen on stuff that's just mounted on a trolley in a production facility that's just wheeled around by users all day, every day, and it gets vibration from the trolley and the wheels and the floors and everything else. And I've seen TO220s completely snap off from such vibration. So this is what these electrodynamic shakers are designed to do. They're designed to test your PCBs to make sure you don't have any mechanical problems, and it can just be in components, it can be joints, it can be connectors, it can be all sorts of stuff. It can be the PCB. Obviously, with modern surface mount stuff like this, like you've got a lot less mass in surface mount components, but you know, at a certain vibrational mode, you could find like a BGA joint could crack under there or something like that, or even one of these connectors, like if they didn't have the big solder pins on them to actually anchor them down to the board, then these would vibrate right off. All these pins in here at a certain frequency and amplitude, they would just snap right off, and that connector would just fall off the board if you didn't have those big solder anchor points on there to change the physical mode of the component. So yeah, that's what this is designed to do. It's basically a electromagnetic speaker, hence the electrodynamic part of it. And this is just going to pop off, and it has, unfortunately, it's broken. So there you go. Oh yeah, oh that's all sticky as. Yeah, that's Gonski. Anyway, here we go. Inside of it. Oh yeah, okay. So that's broken off. We have to fix that. But no wuckers, it's basically just got two wires going into there, and this is just a little compliant mount here. I'm not sure what the range of this thing is. It's probably, I don't know, it wouldn't be 10 millimeters. It's probably like 0 to 5 millimeter. But you can see the coil down in the bottom there. There you go. It's just poking its head above there, but it's basically a giant magnet with a coil. It's just a big grunty speaker that's designed to be, you know, fairly linear in operation over its range with like a mechanical interface like this, because you won't get this with regular speakers with, you know, your paper or fiberglass cone interfaces. So yeah, these things are designed so that they actually have mounting points where you can put, you know, huge metal plates on there, and then you attach your products to those. And the way you analyze the products that they meet specification is you use these accelerometers like this. Now, this is a PCB Piezotronics one. It's one of the big brands in the industry. You know, you can get Brüel and Kerr ones as well, who now own Lin Dynamic Systems. This one's interesting. These are actually tiny little accelerometer, little low mass accelerometer like this. You can get them a bit smaller than this, but not much. You know, this is like one of the real small ones on the market. And what you'll do, you need at least two, usually, is you will mount one of them onto the platform. So you'll stick it down, or either physically mount it, or you'll super glue it. Super glue's very popular for these, by the way, because they fairly rigid mount, and then you can just snap them off later. So you attach one to the plate, so then that you can get the response, the vibrational response. So these are just little accelerometers, very linear, and they're calibrated, and this probably has a calibration sheet. It's completely faded. Anyway, yeah, you get these calibrated. They're really expensive. Sometimes it's more expensive to calibrate them than it is to buy them. But anyway, if you take your quantitative measurements, if you're measuring to like a military standard or something like that, they will have, okay, it's got to survive these sort of vibrational modes. You need quantitative values. But you can use these uncalibrated and still get absolutely fascinating results and see where your products actually have issues and things like that. So anyway, you would get one of these, you stick one to the plate, and then the other channel you would attach to the PCB in a suitable location, so you can actually get what's happening on the board as well. So you can maybe, like if you've got a large board, you might like stick it in various locations on the board, and you might be able to see the board actually flex. Like a tiny little board like this, you really wouldn't bother, but a larger PCB that's only mounted on the corners or something, or mounted on rails, you might put the accelerometer in the middle to see what's happening to that board flex. Like inside a rack, for example, and you might see how that flexes as it's being transported. So you sweep it right over the frequency range from 5 hertz to many kilohertz, depending on which standard you're looking at, and then see if your product A survives, B, how much flex there is, and that has potential long-term implications for your product reliability. So yeah, these are real interesting bits of kit, and they're not cheap. If you have to ask the price, you probably can't afford one brand new, and they don't come up very often second hand. Yeah, I really need to fix that. That's pretty how you're doing. So obviously with this thing, somebody has designed a custom interface, and it looks like because that was like glued in there, I guess they were like using that as some sort of like pump. Like they've converted it into, like, you put a tube on here and it's a vacuum vibration thing, like for a liquid. That's some air interface or something. I don't know, but that's the whole point of these things. Like, you just get the motor and you design your own custom like interface for this, for whatever need you do, and they're incredibly versatile. You can use them for all sorts of stuff, and yeah, obviously I think they've used that for some sort of fluid or air interface thing. So that's rather interesting. And the matching power amplifiers for these things, they can be like insanely expensive, and they can have different test modes, and they can have safety features and all sorts of limit switches that tie into them to stop them automatically. Yeah, because when you get to like the ones that are the size of the car, like I've used, like they have a big fence around them, and you'll have someone there like as a safety person to make sure it's all like everything's safe, and you have to get up on a ladder to climb up on the top, and then you've got like big safety interlocks and things to make sure that it's not going to start vibrating and moving when you're actually standing on there wiring up your stuff and things like that. And these are usually rated in newtons. So yeah, I found the data sheet for this. This is actually the 200 series, but this is like like a really old model, but they still actually do sell this. And as I thought, it has a maximum displacement of 5 millimeters. It goes to 13 kilohertz, and it has up to 17 newtons sine peak range, but it actually does go beyond that to 26 newtons peak if you actually stress it. But yeah, it's the runt of the litter. Alright, got it hooked up to the output of a Yamaha dumpster power amplifier here. It's pretty much all I've got. Feeding the output of the function gen in, I've just got like 5 hertz at half a volt. It is a 2 ohm nominal load, so I don't know if this Yamaha receiver can drive 2 ohms, but it's going to be good enough. No, I could have an input wrong or something. Put another 2 ohms in series with it, so that gives 4 ohms total. Just gives a nicer load for the amp here. I'm pretty sure I can go down to 2 ohms, but meh. So I've now put it on the video aux here, so this should work, surely. Oh, hey, hello. She's moving. There you go. Sweet, look at that. There you go, works a treat. Bobby Dazzler. And I can attenuate that by putting weight on. It'll have a maximum weight limit. It's only got so many newtons to give. Ooh, that's what she said. And of course the volume is going to set the excursion there. Yeah, we can really shake the crap out of stuff now. This is great. Can we go down to 10 hertz? There we go. 10 cycles per second. Count them. 5 hertz. No wuckers. Can we go down to 1? Yeah, nah. So, oh, there we go, 2 hertz. 2 hertz can kind of sort of get through. You can see the roll off of the low frequency roll off of the amplifier here. Yeah, but 5 hertz can certainly do it. But yeah, it looks like it's probably got, if you go check the spec sheet of the amp, it's probably like 10 hertz to, 20 kilohertz or whatever. God, I could play with this all day. So this is basically a 50 watt air cooled jobby, but of course once you go up in power you can put forced air through them, of course, and then, well, the more advanced ones, the power amplifiers and the cooling systems are in gigantic racks taller than I am. So yeah, serious business. But this little one, very cute. This is plenty enough for testing PCBs. So what I need now is a nice little platform. That's fun. Now, I know it's a bit how you doing, but anyway, like, this was literally within arm's reach. It was one of these project cases sent into the mailbag, had like clear perspex on top and then had a PCB on there like that. And yeah, we can shake the crap out of that. Whee! We have a completely offset shaker table now, but that allows me to at least bodge on a small PCB, and we can see if we can do an experiment and break something. And you can hear when it bottoms out. Thank you very much. Alright, so what I've got set up here is an LM7912 voltage reg jelly bean part. Got it on a little perf board here. Only got a single screw. Unfortunately, the other screw hole here didn't quite line up. Couldn't be bothered going out to drill it. So yeah, it's flapping around in the breeze here. And of course, this is going to have a mechanical vibrational mode. And if we hit the resonant frequency, just like that, the famous, what is it? Tacoma Narrows Bridge or something that actually collapsed due to the resonant frequency. We will find that because we've got a mass up here and we've got a long lever, essentially. All the mechanical engineers are laughing at me, but anyway, it will have a mechanical mode. So if we vibration sweep this, we should actually get to a frequency where we actually see it like really violently kind of shake. It'll, at one frequency it'll look like nothing. But if we hit a resonant mode, even in a vertical direction like that, I think we're going to start see it really starting to flap around in the breeze, and that can fatigue the leads and then break it off. I was going to sweep it, but automatically sweep it from like 10 hertz up to a couple hundred hertz, but then I thought, no, let's just manually sweep it to see if we can actually find the frequency where it gets the heebie-jeebies. All right, so let's switch it on. I've got 20 hertz here. We'll increase the amplitude like that. And okay, I'm going to increase the frequency. Well, that's 30 hertz, where 10 hertz increments, probably don't want that. We'll go to 1 hertz increments, 30. I want to see this move side to side. 54. Oh yeah. Yeah, look. Look. 60. 70. 85. Oh, there we go. It's 104 hertz. Oh, it's getting more violent. Check it out. 107 hertz. 108 hertz. Oh, yeah, look at that. Look at that. It's going Burko now. 110. 112 hertz. I think we've found its resonant. And if I go above that, 120 hertz. There we go. It's gone back. So I think we found its resonant point, or one of its resonant nodes. 110 hertz with a couple of hertz window there. About 111. That's a good number. 111 hertz. So I'm going to leave that there. And maybe that will eventually fatigue and just simply fall off. That's the plan. It could be more robust than I think. Maybe I need to increase the amplitude. Increase the amplitude till it breaks. Come on. Whoa, look at that. There's a good 5-6 millimeters at least, like, displacement on that regulator. Wow. Still holding in there though. It'll be fascinating. Monitor the output of this, like, on a scope and see what happens with a vibrational mode on it. But anyway, that's for another video. I'm just trying to get this sucker to break, but we may not get it with this vertical orientation. I think we'll eventually get it, but yeah, nah, we might have to put it horizontal or something like that. Horizontal like that, the poor bastard. Let's go. Has that still got the same mode? Oh yeah. Yeah, she's flapping around in the breeze. Look at that. Wow. It's got the same sort of displacement that we got before. Maybe 7mm displacement there, but it's hanging in there. Mind you, you know, those leads are fairly robust, but like I said, I have seen these. I've never physically seen it, like, actually happen live, but yeah, I have seen products that where the TO220s have snapped off due to fatigue. But that's pretty impressive. That's holding up. Oh, that looks great in slow motion on the GoPro. That's hilarious. Come on, break your bastard. I tell you what, I'm impressed. This must be a genuine national jobby. It's not a rip-off. Just fiddling with the frequency a bit. Well, there we go. That's 98. Yeah, it's different here. I think I can get a 105, 110. Yeah, it comes straight again. At 120. Yeah, look, at 120, there's nothing doing there. Of course, we can mount the board at a different angle, but I'm just curious to see if I can get it to go by doing this. 95. That's pretty violent. Around 95 to 98, something like that. Wow, come on. Okay, I'm going to experiment. I'm going to go down. Whoa. Whoa, yeah, it doesn't like that. You should actually hold this sucker down. Oh, there we go. Got it. Got it. Got it. Got it. Got it. Got it. It's going. It's going. It's gone. It's gone. It's gone. Oh, winner, winner. Chicken dinner. Oh, that is fantastic. There you go. We got it. We got one. There you go. That poor LM7912. Oh, it's come-a-gutsa. And yeah, it's sheared completely off the solder joints there. And, you know, that was like extreme, but you can, I've seen this happen over the span of months. So there you go, that's an electrodynamic shaker, and these are real interesting and useful bits of kit for testing electronics. And I've got a nice little beastie here. I think it does actually come in a smaller one in this range, the 100 series, but yeah, these go all the way up. I'd love to get a bigger one, because like you can't use this little one to like shake a multimeter or something like that. It's just too high a mass, it's too big. You would definitely need a bigger beastie to run that, and, you know, a decent suitable power amplifier. But as you saw, you know, this is like a 50-watt job. So, yeah, just a regular, like, audio power amp does the business there. No worries whatsoever. Like a subwoofer amplifier would be the go for, like, some of the higher power ones. If you don't want to spend the thousands and thousands of dollars for the actual real McCoy stuff. But, yeah, go and try and get a quote for one of these from Brule and Kerr now, who own these, and yeah, if you have to ask the price, you can't afford it. Their gear is just like ridiculously good quality. But, you know, in the military and like high-end fields that I've been in, you think nothing of paying, like, you know, $5,000-$10,000 for like charge amplifiers for like accelerometers that we looked at, and for these shakers and the power amplifiers that go with them, and the test systems and all they've got everything you could possibly need. I mean, they use these things to, you know, shake satellites and cars and things like that. And it's really fascinating subject. So if you want to see me do more videos on this, please give it a big thumbs up and leave it in the comments down below what I can actually test with this thing. But that was a fun experiment. We snapped a TO220. So let that be a lesson to you. Don't leave them flapping around in the breeze. Catch you next time.